You train standard transformers.
They scale with parameters and tokens, locked in a power law dance.
But tokens run thin, high-quality ones, scarce.
You watch them struggle math, code, reasoning tasks.
Stuck, their scaling exponents stubborn, unyielding.
You reach back, dust off an old idea, two simplicial attention.
No more dot products, bilinear, one simplex.
You go trilinear, two simplex, three vectors, one interaction.
QK, K's tangled in a trilinear web.
Plaudits woven from their triple dance, not just pairs.
You need rotation invariants, like rope E, but for 3.
So you borrow from determinants?
The area of parallelograms, volume of parallelotopes.
A trilinear form that bends with rotations, not breaks.
As expressive as the original, but sturdier.
You build it in Triton, optimize the kernel.
2D tiling, merging inputs, overlapping math on CUDA and tensor cores.
520 TFLOPS rivals the fastest attention around.
Backward pass split, no atomic overhead, smooth as silk.
You train it, same size as standard transformers.
Fix the token budget, watch the metrics shift.
GSM 8K, MMLU Pro, MBPP numbers climb.
1B params, 2 simplicial edges out the rest.
3.5B params, the gap widens, unignorable.
You check the scaling laws, the exponents.
Transformers I-plots, 2 simplicials I-leaps.
18.5% steeper for math, 20.2% for hard reasoning.
You realize tokens don't need to scale as fast as parameters.
It's not just better, it's more efficient with what it has.
You say it's just a tweak to attention.
You show the proof, it solves problems standard attention can't.
Not without exponentially more layers.
It's not just a bigger net, it's a smarter way to see relationships.
You step back.
You didn't just build a better transformer.
You built a model that learns more with less token fuel.
A bridge between parameter count and reasoning power.
One that doesn't just scale, it scales wiser.
And you realize
This isn't just about math or code.
it's about squeezing more sense from fewer words.
About making every token count.
In a world where tokens, like sense, are never infinite. Welcome back to the deep dive. That opening monologue, rap, whatever you want to call it. Wow, it really captures that intense energy, doesn't it?
It does, yeah. That kind of almost frantic but focused energy you get when you're deep into a problem.
Exactly, like 3 a.m. staring at the results, hoping for a breakthrough. And today, we are absolutely plunging into that world. We're looking at some really fascinating developments in large language models, LLMs.
That's right.
Specifically, we're unpacking something that sounds like it could, well, fundamentally change how these models learn.
Well, panicked energy from the rap isn't too far off sometimes. Honestly, that was surprisingly accurate. It nails the daily grind.
Right.
You spend all this time, all this effort scaling up these amazing transformer models. They grew beautifully with more parameters. It feels great. You know, more horsepower, it flies.
Yeah.
But then, bam, you hit this wall. It's a data wall. Getting enough high-quality tokens, the really good linguistic fuel these models need, is getting tough.
So it's not just any data.
No, exactly. It's like, trying to make a gourmet meal. You need those rare, perfect spices. You can't just dump in cheap filler and expect the same result. These high-quality tokens are becoming scarce. And that leads to this real frustration. We see these stubborn scaling exponents with standard transformers, especially on the hard stuff, complex math, coding, reasoning.
The supercar hitting the bumpy road you mentioned?
Precisely. You pour in more compute, more parameters, but it just doesn't get much faster or better on those specific kinds of problems without a fundamental change.
Oh, okay.
So our mission for this deep dive is to really dig into how researchers are tackling this token bottleneck. And they're doing it by rethinking the building blocks, specifically with this innovative idea called two simplicial attention.
Two simplicial attention.
Okay. The goal, really, is to make every single one of those precious tokens count for more. Get more bang for your token buck, so to speak.
Okay, that makes sense. So this data wall, if we keep building bigger models, what does this actually mean? It sounds like size isn't the only answer anymore.
You've hit it exactly. For a while, everything was driven by neural scaling laws. These are basically rules of thumb, empirical relationships we saw.
Right, the LND stuff.
Yeah, performance L depends on parameters N and data D. You increase N, you increase D, performance gets better according to these power laws, like LND plus frac BD plus frac BD.
And models like Chinchilla tried to balance N and D based on compute?
Exactly. They were aiming for compute optimal. Scale N and D together, proportionally.
Yeah.
But the huge assumption there was, well, basically infinite data. An endless supply of good tokens.
Which we're now realizing isn't true.
It's becoming a real challenge, yeah. The availability of sufficiently high-quality tokens is the big emerging problem. So this idea that models are purely compute-bound, limited only by our processing power, that's becoming less and less the case.
We're hitting a data ceiling.
We really are. And here's the kicker. Most standard architectural tweaks we've made, they sort of shift the error. They make the model a bit better maybe, but they don't change that fundamental scaling better for data very much.
So you still need tons more data for a significant leap in, say, reasoning.
Pretty much. You need a deeper fix than just minor adjustments.
Which brings us back to this too simplicial attention. So this isn't just another tweak, it's a different way of looking at the data itself.
That's a great way to put it. Think about standard attention. It's basically looking at pairs of things, right? A query and a key. Like word A looks at word B. How relevant is B to A? It's a two-way street, a bilinear form.
Okay.
Too simplicial attention extends this. It makes it a three-way interaction. Now you have a query, a key, and another key. Let's call it key prime, K.
So Q, K, and K.
Yep. Instead of just Plangle math DF key, interaction becomes something like Plangle math BF key. It forms this third-order tensor of relationships.
Like seeing connections between 3 points instead of just 2.
Exactly. Imagine trying to understand, say, a social network. Standard attention sees Alice knows Bob, too simplicial can see Alice knows Bob, and Bob knows Carol, and that connection forms a triangle with specific properties. It captures these higher-order relationships.
Which means it can be more expressive.
Much more expressive. There's recent work showing it can solve problems like this benchmark called Match 3, that standard transformers would need, like, exponentially more layers to even approach.
Wow, exponentially.
Yeah. So it's not just throwing a bigger net, it's weaving a fundamentally smarter net to catch more complex patterns.
Okay, that three-way interaction makes sense conceptually, but you mentioned something about rotation invariance and determinants in the sources. That sounds pretty deep mathematically. Why is that important here?
Yes. That's where it gets really elegant.
Yeah.
So in standard transformers, we use ROPE, rotary position embedding.
Right, to keep track of word positions.
Exactly. ROPE cleverly encodes position so that the attention scores, the dot products, stay consistent, even if the internal representations get mathematically rotated. And think of rotating a picture. The relationships between objects stay the same.
Okay, makes sense.
The problem is, this new three-way interaction, the simple trilinear form, math revugi, math bubi, math Jiecao, it isn't naturally rotation invariant like the dot product is. If you just slap rope E onto it, things kind of break down positionally.
So you need a rope E equivalent for 3 things, not 2.
You got it. And the clever solution was to borrow from geometry. Think about calculating the area of a parallelogram defined by 2 vectors, or the volume of a parallelotope like a slanted box defined by 3 vectors.
Using determinants.
Precisely. These geometric calculations using determinants are inherently rotation invariant, so they developed attention mechanisms based on these determinant forms.
And that worked.
Theoretically, beautifully. There's actually a theorem, Theorem 5.1 in the paper, showing that a two-simplicial transformer using a specific determinant-based attention can perfectly solve that complex Match 3 problem. It really shows the potential power.
But did they use that in the actual experiments?
The practical side. Well, for the backward past the learning part, they actually stuck with the simpler trilinear form. The determinant one, while theoretically neat, is computationally much heavier, like 1/9 versus 6.
So a classic trade-off, theory versus practice.
Yep. Balancing elegance with efficiency.
Okay, so the math is cool, the theory holds up, but making it work efficiently. You mentioned it could scale cubically. MathCal N3, that sounds like a killer for long sequences. How do they get around that?
Yeah, MathCal N3 is a non-starter for real-world LLMs. You'd never process a decent-sized document.
Right.
The key was using a sliding window approach.
So it doesn't look at everything interacting with everything else.
Exactly. Each query only interacts with keys and key primes within a certain local window, maybe like 512 tokens for keys and 32 for key primes or something like that.
Limiting the scope.
Right. This brings the complexity down dramatically, from cubic to something like MathCal at times W1 times W2, where 1, 1, and W2 are the window sizes. Suddenly it becomes practical. They show that even for really long context, like 48,000 tokens, they could make it computationally comparable to standard attention with the right window sizes.
That's clever. But still, implementing this three-way thing efficiently on a GPU, that sounds like an engineering challenge.
Oh, absolutely. It was a significant engineering feat. They used Triton, which is a language from OpenAI, for writing highly optimized GPU code, building on things like flash attention. They use smart techniques like 2D tiling and rearranging the math turning the tricky QKK interaction into operations that GPUs are really good at, like matrix multiplications.
Yeah.
They managed to get the GPU cores working together, overlapping computations.
And the performance.
Really impressive. They hit around 520 TFL OPS, which is right up there with the fastest optimized standard attention kernels like Flash Attention v3.
Wow. But what about the backward pass? You mentioned that was tricky.
Yeah, the backward pass was the real headache. When you have three things interacting, figuring out how errors flow back involves aggregating information across all three dimensions. This usually leads to lots of atomic operations on the GPU.
Bottlenecks, basically.
Exactly. Little sequential operations that slow everything down. Their fix was really smart. They actually split the backward pass calculation into two separate steps, two different kernels.
To avoid the atomics.
Precisely. Even though it meant doing a little bit of recomputation, it ended up being faster overall by avoiding those costly atomic clashes. They also used techniques like grouped query attention to help with memory access. It just shows how much deep optimization matters for these new architectures.
It really does. Okay, so the concept is solid, the math checks out, the engineering is, frankly, amazing.
Yeah.
But the big question, did it actually work? Did it deliver on that promise of better token efficiency in the real world? What did the experiment show?
Right. The proof is in the pudding, as they say. So they trained mixture of experts models, MOE models, ranging from 1 billion up to 3.5 billion active parameters.
Active parameters, meaning not all parameters are used for every token.
Correct. That's how MOE models work. And crucially, they didn't replace all attention layers. Just every fourth layer was a too simplicial attention layer.
Spreading it out, okay. And the tasks.
They focused on benchmarks that really stress math, reasoning, and coding exactly where standard transformers hit those scaling limits. Things like GSM-8K for math, MMLU, and the tougher MMLU Pro for general knowledge and reasoning, and MBPP for Python coding.
And the key finding.
The key finding was clear. Too simplicial attention showed a more favorable scaling exponent that alpha value related to parameters, meaning as the models got bigger, the ones with too simplicial layers improved faster on these complex tasks.
Faster than standard transformers of the same size.
Yes. Interestingly, they noted no gains for the smaller models below 2 billion active parameters. It seems the benefit really kicks in at larger scales.
Okay.
But for the 2 billion and 3.5 billion parameter models, they saw a significant decrease in negative log likelihood, which basically means much better performance, lower error rates.
Can you quantify that steeper slope?
Yeah, they provided specific numbers. For example, on GSM-8K math problems, the scaling exponent alpha was 18.5% steeper for the two simplicial models. On MMLU Pro, the hard reasoning benchmark, it was 20.2% steeper.
That's quite a difference.
It really is. It's solid empirical evidence. And the big implication, going back to our bottleneck, is that with this approach, tokens don't need to scale as fast as parameters. The model gets more efficient with what it has. It learns more effectively from the data it's given, especially when that data is limited.
Wow. Okay. So this deep dive has really taken us on a journey from this looming problem of, running out of high-quality training data.
The token bottleneck.
Right. To this really innovative solution, too simplicial attention, that doesn't just try to brute force scale, but offers a smarter way to see relationships in the data.
Exactly. It changes the scaling dynamics.
It feels like it fundamentally alters how LLMs might grow, especially in a world where good data is precious.
That's the core takeaway, I think. The main contribution is building a model architecture that genuinely learns more with less token fuel. It's about making every token count, squeezing more insight out of the data we have.
Are there limitations? Is it ready for prime time?
Well, like any cutting-edge research, there are next steps. The Triton kernel, while fast for research, probably needs more work for full production deployment. And really unlocking the potential might involve co-designing it with future hardware accelerators. It's still early days in that sense.
But the potential is clearly there.
Absolutely.
So thinking bigger, what does this all mean? We live in this world overflowing with information, but maybe starved for actual sense or insight. High-quality data, like high-quality insight, feels finite.
That's a deep thought.
This work reminds us that real intelligence, whether artificial or human, isn't just about consuming more information. It's about making more sense from less. How might this push us to think differently, not just about building AI, but about how we as humans pursue understanding in this information-rich but maybe sense-poor world?